Good day, I am Cromwell Hopilos. We are going to solve the problem 1.34. A steel pipe of 300 mm outer diameter is fabricated from 6 mm thick plate by welding along a helix that forms an angle of 25 degrees with a plane perpendicular to the axis of the pipe, knowing that the maximum allowable normal and shearing stresses in the direction respectively, normal and tangential to the weld are 50 megapascal and 30 megapascal. Determine the magnitude P of the largest axial force that can be applied to the pipe. So the given is the normal stress, 50 megapascal, multiply it by exponent 6 to convert it into Pascal. Same goes with the shear stress, 30, so 30 times 10 raised to 6 Pascal. And the angle, 25 degree, and the thickness is 6 millimeter converted, so 0.006 meter. And the outer diameter converted 0.3 meter. Now the outer radius is just the divisible of diameter, so diameter divided by 2, so 0.15 meter. Now we don't have the inner radius, but we can get it by subtracting the outer radius and the thickness. So based on the top view, so this is the top view. Here is the outer diameter, right? Outer diameter. So the radius of the outer, now this is the outer radius. So in order to calculate the inner radius, you should subtract it, the outer radius and the thickness, which is 0.006. So we will get 0.144 meter. In order to calculate the area, this is the formula. So pi r is the cross-sectional of this cylinder. So this is the top view. So this is only the cross-sectional. So pi 0.150 squared, 0.144 squared, we will get this answer. Let's review the stresses on an inclined plane. So assuming that this is the steel in the problem, here this is the normal plane on the applied load. So the plane is inclined. You can see the load is also changing. The area is also changing. We call it A prime. So in order to calculate the A prime, let's focus on this. So this is the A prime, or the new area with respect to the angle, and this is the original area. To calculate the area, we relate it to the cosine, which is the opposite, the adjacent over the hypotenuse. So the adjacent is the original over the hypotenuse. Transpose. So A over cosine, A over cosine. A original over cosine theta. Now let's focus on the load. Is the distributed load P. So it divided into two components. So Pn is equal to, so this is the angle, so this is the adjacent, right? So cosine theta times the original P, and sine, and the shear stress is sine theta original P. So this is why when the plane is normal, the shear stress is also 0. So when you input the angle 0, sine 0 is equal to 0. So that's why shear stress is 0. In inclined plane, the shear stress is equal to Pn over A, right? We know that the Pn is cosine P. So P cos theta, and A1 is just A sine. So it becomes this. So shear stress on the inclined plane, Ps, which is equal to P original sine theta. So P original sine theta, and A1 is A over cosine. Reciprocal. Now we have this formula. So the formula at 50 megapascal, we will use this. So P is required, so we will isolate the P. So cross multiply, we'll arrive at this answer. Same goes with the shear stress on an inclined plane. We isolate the P. But you can see sine is 2 theta. But here is sine theta cos theta. We can, this problem, we can multiply just it by 2 over 2, which is just also equal to 1. So it does not violate. So we know that 2 sine theta cos theta is equal to cos theta, sine 2 theta, right? So we will get this sine 2 theta over 2 PA, right? Now, we solve it for P, so this will arrive at this answer. So let's input and calculate. For the solution at 50 MPa, for this is the normal stress. This is the formula. Input, so this was the area, and the shear stress, the original at the normal plane, so 50 times 10 raised to 6. This was the angle. So the answer is 337. And for the shear stress at equals 30 MPa, so this was the formula. Input to same area, 5.54 times 10 raised to negative 3. 30 times 10 raised to input the theta 25. So this will become sine 2 times 25, so 50 degrees. 50. Final answer is P max, since P max is the smaller value of between these two. So P max is just equal to 337 kilonewton.